is catch up with the train.
We can't be far behind.
Do you hear that?
We must be getting close.
Hold on.
We finally made it to the last unit. We talked about Galileo with kinematics. We had Sir Isaac Newton with forces, James Prescott Joule with energy. We had Werner Heisenberg with momentum. For those of you that chose to do the optional one, we talked about Baron Kelvin with thermodynamics. We had Louis-Victor Pierre-Armand 7-2 de Broglie with our waves unit. We had Charles Augustin de Coulomb with electrostatics. We talked about Georg Simon Ohm with circuits, Nikola Tesla with magnetism, James Clerk Maxwell with the electromagnetic spectrum. We did Einstein's relativity, and now we're left with nuclear physics. And so we just have to click on the face of Ernest Rutherford right here and begin. We've eased into this topic already by talking about the history of light and then particle-wave duality, and then building up this idea that light is not really just a wave, it can also be thought of as a particle, and that particle of light we call a photon. And so we've already discussed what the photon does in terms of atoms. You're able to treat that photon like a genuine particle that collides with electrons and knocks them either to higher orbital shells or out of the element entirely. And so the photoelectric effect is sort of an interesting aspect of that setup on a larger scale. So imagine that you've just got some tube that's just a vacuum. Nothing inside there, not even air. On one end of the tube, you've got a piece of metal which is connected to a wire. That wire runs out of that tube through an ammeter to some variable power supply, so a voltage source that we can tune to be either nothing or really positive or really negative. And then that wire just terminates in the other side of this tube and doesn't connect back. So we've got an open circuit right here. What you'd find, and what Heinrich Hertz found as part of his experiments, is that there is certain types of light that can be shown on this piece of metal right here, so that this ammeter actually gives you a reading. And this is called the photoelectric effect. Thinking about this classically, though, with a mind towards classical physics, this should be a puzzling result. There shouldn't be any reason for the electrons to travel through that empty space to the other side unless there's some kind of force or a field or a potential, not just light hitting that material. And so it took a lot of great minds and a lot of time. This was originally found by Heinrich Hertz, and it was like 100 years later or so when Einstein was able to explain it. And this explanation that he gave was what won him the Nobel Prize. It's treating light as a photon, as a genuine particle, and those photons come in, hit the electrons that make up that material, and send them across the tube. But it doesn't work for just any light. If we increase the intensity on this 742 nanometer red light, nothing happens. We increase the intensity up as far as we can go. We have as many photons coming through as possible, but nothing's happening. And the reason why is because of Planck's quantum hypothesis, that formula that we learned with the photon when we first started studying it. E equals hf. If we want these electrons to go across, we need to put in the right amount of energy. We need to put in enough energy to ionize those electrons and send them to the other side. And the only way that we're going to give them enough energy is to increase the frequency or decrease the wavelength. And so what we have to do is move from the infrared up to ultraviolet. And as we sweep across, we find that there is some point where electrons begin to move, and we get a reading on our ammeter. One thing that would be nice to look at would be a graph of energy for these electrons versus the frequency of light. And so this program is going to build one on the right-hand side here. And we can see that as we have a really low frequency or a high wavelength, we don't have any energy at all. The electrons don't even care that light is hitting them, because in fact the light is pretty much just passing right through. And as we increase that frequency, we see that we are still at zero, still level and level and level, but there's some point where we begin to move up off of the x-axis, and then at that point, as we increase our frequency, we get a line that travels pretty much linearly off to one side. So it's as if our function is 0, 0, 0, 0, 0, 0, 0 until some point where we find that magical frequency, and then it becomes linear. Our first discovery is that there's some threshold frequency that you have to achieve. There's a minimum amount of frequency that you need for this process to work. And if you're below that, nothing happens. The electrons stay right there. If you're above that energy, if your incoming photons have more than that threshold frequency, then the electrons just have more energy to travel across. But there's another way that we can look at this. We could instead choose a frequency that we know works already, like 400 nanometers, and we can put in a battery. So here I've applied 8 volts to this system. And so now as these photons come in and collide with electrons, any electron that's removed from the atom is going to be in empty space here, and it's going to be influenced to the right. It's going to be pulled to the right by this voltage. And so if we turn the intensity up, we can see that that's exactly what happens. These electrons are kicked out and moved to that right-hand side, and we know they are because we have a current that is reading right here. But now as we decrease this voltage from 8 to 0, things stay constant. But once we get to 0 and start working to the other side, now the left plate is positive and the right is negative. So the electrons that get kicked out, they're going to get pulled back to the left. And so we can keep decreasing this dial until we have exactly a current of 0. And even though you wouldn't be able to see this in reality, it's as if those electrons get kicked out of the atom and they fly across the tube and across the tube and across the tube and then fall back in. So there's some voltage that we can apply, which we call a stopping voltage, that stops the flow of current. These two properties, your threshold frequency and your stopping voltage, they depend on the material that you're using. So the left-hand side here, we had originally sodium that was on there, and now I've moved that target metal to zinc. And we can see at the 400 nanometers before would send electrons across. Now it's not really working, so we have to increase that frequency to give us a value that is much larger. And so now if we go to about 240 nanometers, we have electrons that are traveling across, and so we do have current. And we could again find that new stopping voltage by bringing this down and finding where the current just begins to stop, and we see that this stopping voltage is different as well. So those two properties that we're talking about, your threshold frequency and your stopping voltage, they depend on the material that you're using in your setup. So again, in this setup of the photoelectric effect, there's two properties that really matter. There is the threshold frequency, which is the minimum amount of energy you have to put in to have current flowing through. And then you've got stopping voltage, which is the voltage that you can use to just cut off that current. And the stopping voltage is really just one number. It's the moment when that current stops. And so it's essentially that moment when you've applied a voltage so that we have enough energy coming in to knock those electrons out, but they don't actually go anywhere. And so effectively what you're finding with that stopping voltage is the energy that's required to ionize that atom, to kick the electrons out. And even though they don't go anywhere, you did have enough input energy to actually move them. And so another way to think about this is with this formula right here. You can say that the energy of the incoming photon is equal to the kinetic energy of those photoelectrons, the electrons that are kicked out of the material, plus this thing called the work function, or how much work you would need to do to actually move the electrons from the ground state out of the atom. So the simplest case for working with this formula, E equals Ke plus W, is when the electrons don't have any kinetic energy at all. They are able to be removed, but they don't actually travel across the tube. So this is the case when you've met that stopping voltage. So if we look at one of my favorite websites, Hyperphysics, we can see that they've listed a bunch of work functions for the photoelectric effect. They say down here at the bottom that zinc has a work function of 4.3 electron volts. Let's see if we can figure out what type of energy then is needed to just get the electrons to move, but not to actually create any current. All right, the plan is to find out what type of light is required to just get those electrons move but not have any kinetic energy. And that's the case when E is equal to that work function. And we already know for our photons, the photon energy is found by hf, Planck's constant, times our frequency. So if we're saying that E equals W, because our Ke is 0, then we can also say that hf equals W, or at the end of this whole thing, we're just going to take our work and divide by Planck's constant, and that will give us our frequency. So our work is 4.3, and we're dividing by Planck's constant, which in electron volt seconds is 4.14 times 10 to the minus 15. And so our answer for frequency is right here, 1.04 times 10 to the 15th. The next thing that we want to do, though, and this is just because we're working with PhET, PhET reports those numbers as a wavelength instead of a frequency, so let's convert this into a wavelength using the wave speed equation. We know that our wave speed equation is v equals f lambda, and because we're talking about light, that speed, that v, is going to be the speed of light. So we're just going to take the speed of light, which is 3 e to the 8, and divide by that frequency. And there we have it. We've got our wavelength, 2.89 times 10 to the 7th meters, or if we convert this, 289 nanometers. So let's jump back over to PhET and see if that makes some sense. All right, I plugged in the 289 nanometers as we calculated, and so we've got 280 nanometer light hitting some zinc plate, and nothing happens, which is exactly what we should be expecting, because we've applied enough energy to ionize those atoms to remove the electrons from all their orbital shells, but then they don't have any kinetic energy, so they don't go anywhere. They don't have a speed with which to travel, so we don't see them travel across this plate. If we were to change the light that we have, though, and put in something with less energy, meaning a larger wavelength, we should again expect nothing to happen. But if we put in something with more energy, meaning a larger frequency or a lower wavelength, then maybe we'd see some results. So instead of 289, what if we put in just one step below, 288? Now we can start to see those electrons beginning to travel across. So they have just a little bit of kinetic energy with which to move, whereas at 289, we had that magic window where we applied just enough energy to overcome that work function and nothing else. Let's do one more of these and call it a day. So let's say that we have calcium as a sample we're shining light at. And we can see on hyperphysics that calcium has a work function of 2.9 electron volts. Try to calculate how much energy would be required to just overcome that work function for calcium, and use that to figure out what type of light we would have to shine at calcium in order to overcome this work function.
I wanna be the very best, like no one ever was.
The only difference for this problem is the work function. The whole idea is the same. We want to find out how much energy we need to apply to just overcome that work function, but to not have any kinetic energy. So all I'm going to do is just change this work function in my table from 4.3 to 2.9. And we find that we now get a frequency of 7 times 10 to the 14th hertz, or about 428 nanometers. And so if we look at the electromagnetic spectrum from our reference table, we find that 7 times 10 to the 14th hertz falls somewhere in this violet band. So we're going to need violet light in order to have the electrons overcoming that work function. And anything that is more violet-y than violet, namely ultraviolet, is going to work. Anything less, blue, green, yellow, orange, red, infrared, those aren't going to work. And so here's the picture. We've got 428 nanometers plugged in and nothing's happening. But if we increase this frequency and lower the wavelength, then we do begin to have some movement of those electrons moving across. So let's just add one other piece to this. What if we instead choose a incoming frequency, like maybe 270 nanometers? Let's find out how much kinetic energy these electrons actually have when they're shining against calcium. The setup is we have a calcium plate that is being bombarded by 270 nanometer ultraviolet light. Those electrons are going to get kicked out as long as they are able to overcome that work function that calcium has of 2.9 electron volts, and whatever energy is left over is going to be their kinetic energy. So for me, the first step is going to be calculating that wavelength from 270 nanometers into just meters. And the way that we're going to do that is by remembering that each nanometer is 1 times 10 to the negative 9 meters. And so this is our wavelength converted into just plain old meters. Now what I'm going to do is I'm going to find the frequency. We can get energy directly using E equals hc over lambda, but just for fun, let's find that frequency by doing the speed of light, 3e to the 8, divided by our wavelength in meters, and that will end up giving us 1 over seconds, which is a hertz. So we've got 1.111111 times 10 to the 15th hertz. Now we're going to have to find that energy, and we can find that photon energy, the energy of that incoming 270 nanometer light, by doing E equals hf. So we're going to take our Planck's constant and we're going to multiply by that frequency. And this is our energy, 4.6 electron volts. And it's in electron volts because we use the electron volt seconds Planck's constant. There is the other one that you could use for joules, but because our work functions in electron volts, we might as well just keep everything consistent. So now the last step is to get that kinetic energy. That kinetic energy, if we take our original photoelectric effect formula, it's going to be E minus W. So the energy that we just found minus the work function that we have to overcome. And so each one of those electrons has an energy of 1.7 electron volts. The last step, if you'd like to, is to convert this into joules. And so we need to remember that 1 electron volt, if I click on the right spot, 1 electron volt is 1.602 times 10 to the minus 19 joules. And so this is our value in joules. This was our wavelength in meters, and so this is our value in joules. And then we could do whatever we wanted from this point. We could, for example, find the speed of this thing. And so using our kinetic energy formula, we could calculate our velocity. That is just going to be the square root of 2 times our energy divided by the mass of the electron, which you may recall is 9.11 times 10 to the negative 31. And so look at that. These electrons are really cooking as they move across. That's like 773,000 meters per second. Pretty darn fast. And that's because 270 nanometers of ultraviolet light is pretty energetic light. You've got ionizing radiation at that point, which we've talked about in a warm-up problem. And that's the whole game for the photoelectric effect. You've got E equals KE plus W. Photons come in, and they hit those electrons. If you're able to overcome the work function, the electrons leave the atom and go across and create some kind of current. And if they don't have enough energy, nothing happens.
This seems like magic.
Yeah, it's just a solar panel.
Solar nano, solar panel, solar power, solar power, solar panel, solar panels.
Solar panels.
There are other ways that photons interact with matter, though, and that's going to be our video next time where we talk about Compton scattering.